In this problem, we're asked to find the Thevenin equivalent of this source circuit to the left of the interface, shown here, and then use the Thevenin equivalent to find the voltage delivered to the load. We did this problem earlier, but I'll just give you the final result, and I'll post the derivation of this equation, which is described as VT is VOC equals just 1/3 of VS1 plus VS2 plus VS3. So I'll derive this relationship at the end of this video, which is recorded earlier this lesson. Now let's find the R equivalent associated with this circuit, and that's basically looking back between terminals A and B. So we want to find R equivalent, and what that implies that we just saw in a previous video is that we short out all the independent voltage sources and current sources. Since we just only have voltage sources, we'll just short out VS3, VS2, and VS1. And when you look back, we see that this R is in parallel with this R. So we have R in parallel with R, and that's equal to R times R over R plus R, or R over 2. But these two R's results in R and 2, which is in parallel with this R. So R over 2 is in parallel with this R, so therefore that's R over 2 times R divided by R over 2 plus R. That yields R over 3. So our equivalent resistance is just equal to R over 3, which is our Thevenin resistance. So redrawing these circuit, we have VT, which is just 1/3 of all the sum of these voltages, replaced with 1/3 of the resistor R for each of these resistors. And we have a load of RL. Now the voltage delivered to the load is just simply, since this is V, that's plus and minus, is a simple voltage divider, which is just RL over R over 3 plus RL times VT. We'll substitute VT that's 3RL plus R, where we multiplied 3 top and bottom to give us this relationship here for the R. So for the resistance, it's 3RL over 3RL plus R, and for VOC, it's 1/3 times VS1 plus VS2 plus VS3. The 3's cancel, and we're left with V delivered to the load is RL over 3RL plus R times VS1 plus VS2 plus VS3. And that concludes the derivation or analysis of this problem. The next video will show you how I derived this equation, and this was shown on a previous video on superposition. Here we have 3 voltage sources, and we want to find the output. So the first thing we need to do is, let's say we want to find the output due to VS3. Well, we need to short out VS1 and VS2. So let me copy this circuit edit, copy, edit, paste. So here we have this voltage, same circuit. Now let me erase. And we want to replace it with a short. Okay, now we have the voltage due to VS3. We see that these two resistors now are in parallel, and we can see that we can use the voltage divider of VO. So we can redraw this circuit now as VS3 goes through the resistor R, and then the two parallel resistors becomes half of the resistor. So in other words, we have R here and R over 2. The R over 2 comes when, because these two resistors are in parallel, and when two resistors are equivalent, is R times R over R plus R, which is just equal R over 2. So we can see here VO3, the output due to voltage source 3, is simply using voltage divider, is VS3 is the source, and the output is just R over 2 R plus R over 2, and when you simplify that, that's just 1/3 VS3. So VO3 in summary is 1/3 VS3. Now you can see, because of symmetry of the circuit, if I want to find the output due to VS2, the second voltage source, we just short VS3 and VS1, and we'll get VO2 is equal to 1/3 VS2, and we're going to get the same relationship for the voltage source VS1. So this is VO1 is equal to 1/3 VS1. So the total output is due to each of those voltage outputs due to source 1, voltage source 2, and voltage source 3, or 1/3 VS1 plus VS2 plus VS3. So that's our total output in this case. Okay, so we can see it acts like a summer. So that's how you use the concept of the superposition principle to simplify our analysis in terms of analyzing this circuit.